So hi all, I am Meet Sharma and this is ELL 101 project on the topic power grid system. Now many of us would have wondered how electricity reaches our home. The answer to this question is a large electrical system called the power grid system. Although it may look complicated, but it uses simple electrical components like transformers. It has to be highly efficient in order to ensure that the energy that was present in moving water, air or steam just a few milliseconds ago is transferred instantly to cater to the needs of our home electrical appliances. In fact, the power grid system is the largest electrical system in the world that can span over a complete country. In fact, India has only 5 such power grid systems which are shown in this map. The main advantage of large power grids is reliability. They can supply power even when some of the generators are stops functioning because all the generators are interconnected. Now the components of a power grid system. The power grid system may look complicated, but its components can be divided into three parts. That is the generation, transmission, and finally distribution of electricity. Each component has different voltage values. The transformers are very essential device that act as bridge between the different components. Transformers are in fact the backbone of the whole power grid. Without transformer, it wasn't possible to construct such a complicated power grid. They are used in every step. Now another question is what kind of current is used. Now the alternating current is used in the power grid as it solves the biggest problem that is faced during the transmission of power. That is the I square R losses, which considerably decrease the power output for long distance transmission. With the help of transformers, which work only for AC current, we can decrease the value of current without any change in the power, which considerably reduce the losses. We can't do so with DC. Also in 19th century, initial attempts for making a power grid were made through DC only, but it was found that with such a large value of constant current, the power loss was so much that in long distance the power was completely lost. That's why AC is used. Now the first step in power grid is the generation of electricity. Electricity is produced in the power grid with the help of a device called a generator in power plants. The AC generator is used for this purpose. Now the design of the AC generator is similar to a DC generator, except that here the commutators used to change the direction of current in armature are not used. Now in a DC generator, the rotatory part is called the rotor, and it consists of field windings that are powered by a separate DC generator. These field windings produce a magnetic field around them. The stationary part called stator consists of armature windings. Now if the rotating part is rotating with n rpm, then the frequency f of the EMF induced in the stationary part, which is the armature winding, is given by np by 120, where p is the number of poles in the rotor. Now if the flux through the armature windings is varying sinusoidally, like phi is equals to phi m cos omega t, then by Faraday's law the EMF induced will be given by E is equals to phi m omega sin omega t. Now here as there is no commutator, as in the case of DC generator, without a commutator the output will be a sinusoidal AC signal E. Now in reality, three-phase supply is used instead of a single phase supply. In this, the power is produced in three sources, each having the same amplitude but each having a phase difference of 120 degree with each other. Three-phase supply is used because it supplies constant power, leading to less power losses, and also the amount of wire is reduced. Now typical three-phase supply generator is shown, in which the three sources are connected through the armature winding, and the magnetic part rotates. Now when the magnet rotates, the voltage will get induced in all the three coils. It will be of same magnitude but out of phase to each other by 120 degree. In ABC sequence, which is also known as the positive sequence, the phase voltages will be given by this. We see that each phase voltage differs in its phase by 120 degree to each other. The relation between the line current, that is the VAB for the first line, and the phase voltage is given by VAB is equals to √3 VA dash. This is the relation between the line voltages and the phase voltages for a three-phase supply. Now the next step in the power grid is the transmission of electricity. Now after the electricity is produced, the main challenge is to transfer this through very long distances. Here the problem of I square R losses arises. But as the current is AC, we can alter the value of current by changing the value of voltages by the help of a transformer. Now transformer is basically a magnetically coupled circuit in which two coils are wound together across a core. If we assume that there are no flux losses and there are no power losses, then we see that the voltage induced in both the coils is proportional to the number of turns in the coil, and the current in them is inversely proportional to the number of turns. By the help of this, we can alter the value of the voltages by just changing the number of turns in the coils. Now in reality, for a practical transformer, there will be some power losses and some flux losses which cannot be neglected. The equivalent circuit of a practical transformer is as shown. The leakage inductances LL1 and LL2 represent the flux losses in the transformer, and the resistances R1 and R2 represent the I square losses, also called as the copper losses. The iron losses or the core losses, which are the eddy current loss and the hysteresis loss, are represented by the resistance RC. The transformers are usually rated in volt ampere reading and frequency ratings. The frequency is selected to be not so high in order to reduce the reactance equal to omega L of these inductances to reduce the copper losses. Now in reality, as the supply is in three-phase, a three-phase transformer is used, which consists of three magnetically coupled circuit in which primary side and secondary side are connected in different connections. The most common connection is the delta Y connection. In the delta Y connection, the primary coil is connected in a delta manner and the secondary coil is connected in the Y connection. In this, the relation between the line voltages of the primary coil and the secondary coil are given by V2 is equals to root 3 N2 by N1 times V1. This kind of connection is mainly used in power transformer at the beginning of transmission for the step-up operation. Another type of connection that is used is a Y-delta connection. In a Y-delta connection, primary one is in Y connected and the secondary coil is delta connected. Here the relation between the line voltages is given by V2 is equals to N2 upon root 3 N1 times V1. This type of connection is used for step-down operation at the distribution substations. Practical transformer. Now in a practical transformer, the efficiency, voltage regulation and the area product, that is the product between the window area and the core area, are given by these relations. Now in a practical transformer, thin insulated laminated steel is used as a core as lamination into thin sheets decreases the eddy current losses. While oil is filled in the transformer to act as a coolant because the resistance decreases with temperature and so copper losses will be decreased. Now we see power transformers. Now in a generating power plant, the AC current are produced in a typical range of 1 to 1.1 kilovolt. But for transmission, these voltages are stepped up by transformer called the power transformer to very high values like 400 kV, etc. in order to reduce the current. For this purpose, a type of transformer, power transformer, is used. It typically has a volt ampere reading of 200 megavolt ampere. Now if we see that as volt ampere reading is very high, it will have a very large window area and core area, and hence it will be a very large transformer. We can see in the image also. They have a very high efficiency of around 97%. They can be used for both step up and step down transformers. They are generally used for transmission of high voltages, and in them delta Y configuration is usually used for step up operation. The next step is transmission lines. These form the bulk of the power grid circuit. They generally carry very high voltages which can be greater than 400 kV. So it is unsafe for them to be close to the ground. So these lines are connected very high above the ground. Also, as they are exposed to the environment, there is a risk of breaking of wires due to winds. That's why the wires are connected by dampers that reduce the oscillation of the wire due to winds. The next step is distribution substations. Now distribution substations are actually those areas in a power grid which receive the power that is sent by the transmission lines. Well, they generally use power transformers to step down the voltages that operate at high voltages. That step down power transformer used here generally have a typical power rating of 220 kV to 2 to 110 kV and a volt ampere rating of 5 to 150 MVA. The low voltage AC produced by them are transferred to street overheads where they reach distribution transformer, which again step down them to the normal voltage value of say 220 volt. There can be a large number of such substations along the transmission line which are used for a variety of purposes like switching. They can also be used for if for example a fault has occurred on one of the transmission lines, these substations can be used to switch off that line so that there is no effect of that fault in the rest of the power grid. So in a way, this is another advantage of having a large power grid. Here the Y delta connection is usually used in the power transformer. For some industrial consumers, the power is fed directly into the substation. For others, it is transferred to distribution transformers. There is one more reason by which power can be lost in a power grid, which is the power factor. Now we see that the power is given by P is equals to VI cos theta. Now if the value of the power factor cos theta is very low, a large amount of power will be lost due to the reactive power. Now as the loads are mostly inductive, the current lags the voltage, resulting in power losses. Power factor correction is usually done by connecting a suitable capacitance in parallel to the load. This improves the value of power factor. Power factor correction can be done at the devices, and the devices used for this may be at the central substation or spread out all over the system. These devices usually consist of large number of capacitors that are switched on by regulator, which measure the power factor of the incoming supply. Now this figure shows a simple device that is used to correct the power factor. We can see that there are a large number of capacitors present in it. The last step in the power grid is finally the distribution transformers. They are the last step after which power supply ultimately reaches its destination. Normally they have a rating of less than 200 kVA. As we can see that the volt ampere rating is quite less than power transformer, so they are very smaller in size as compared to the power transformer. They usually operate at loads that are quite less than full load. The typical voltage rating is 11 kV to 240 volt. The flux density is also less than the power transformer. The efficiency of a distribution transformer is generally less than the power one. Now the load is less, iron losses dominate over copper losses. So the laminated cores greatly improve the efficiency of it by reducing the eddy current losses. They generally operate throughout the day. They can be single phase or three phase depending upon the need of the user. Their efficiency is generally judged from all day performance. In India, 220 volt and 50 Hz supply is used. Finally, electricity reaches our home and the power grid circuit is completed. So thank you all.